In the darkest depths of prehistoric time, when the earth trembled beneath colossal footsteps and the skies echoed with thunderous roars, there existed titans beyond imagination. For over 160 million years, dinosaurs ruled this planet with absolute dominion, their massive forms casting shadows across primeval landscapes that stretched beyond the horizon. But then, in a single catastrophic moment 66 million years ago, everything changed forever. The asteroid that ended the Age of Giants didn't just wipe out the dinosaurs. It opened the door to a new world, a strange and alien Earth, where the survivors would have to adapt, evolve, and fight for their place in the hierarchy of life. What emerged from the ashes wasn't just smaller creatures scurrying in the shadows. What rose to power were beasts so bizarre, so terrifyingly magnificent, that they make today's apex predators look like house pets. Welcome to Ancient Dreamser, where we uncover the forgotten chapters of Earth's most incredible stories. Today, we're diving deep into the age that followed the dinosaurs, a time when the planet belonged to creatures that most people have never heard of. Giants that stalked the land with jaws powerful enough to crush bone, predators that soared through ancient skies on wings spanning the length of school buses, and marine monsters that turned the oceans into hunting grounds of unimaginable terror. Here's what's going to blow your mind. The story you think you know about prehistoric life is incomplete. Everyone talks about T-Rex and Triceratops, but the real monsters came after. For the next 60 million years following the Great Extinction, Earth became a testing ground for evolution's most extreme experiments. We're talking about mammals that grew larger than elephants within just a few million years, birds that stood 10 feet tall with beaks like battle axes, and marine reptiles that made the megalodon look like a goldfish. But here's the thing that makes this story even more incredible. These weren't just random creatures stumbling around a post-apocalyptic wasteland. These were intelligent, perfectly adapted killing machines that dominated their environments with surgical precision. Some of them developed hunting strategies so sophisticated that modern predators still use variations of their techniques today. Others evolved defense mechanisms so effective that they survived for tens of millions of years, virtually unchanged. What I've spent months researching for this video will completely change how you think about prehistoric life. We're going to explore 5 distinct time periods, each dominated by different groups of creatures that rose to fill the void left by the dinosaurs. And the evidence we have for these animals isn't just scattered bone fragments and educated guesses. We have complete skeletons, fossilized skin impressions, and even preserved stomach contents that tell us exactly what these monsters were eating. The first thing you need to understand is that the world immediately after the dinosaur extinction was nothing like the Earth we know today. Picture a planet shrouded in darkness for months, where ash and debris from the asteroid impact blocked out the sun, temperatures plummeted, plants died en masse, and the entire food chain collapsed. Only the smallest, most adaptable creatures survived this nuclear winter scenario. But survival was just the beginning. Within a few 100,000 years, something remarkable started happening. The mammals that had spent 160 million years hiding in the shadows, never growing larger than a house cat, suddenly found themselves in a world with unlimited opportunities. No massive predators stalking them, no giant herbivores competing for food sources, and vast empty ecological niches just waiting to be filled. This is where our story truly begins, because what happened next defies everything we thought we knew about evolution. Instead of gradual change over millions of years, we see explosive diversification happening at breakneck speed. Mammals began growing larger at rates that paleontologists once thought impossible. Within just 5 million years after the extinction, we have evidence of mammals weighing over 100 pounds. By 10 million years later, some had reached the size of modern bears. But size wasn't the only thing changing rapidly. These early survivors were developing completely new body plans, new hunting strategies, and new ways of moving through their environment. Some took to the trees, developing the first true climbing adaptations we see in mammalian evolution. Others headed for the water, beginning the long evolutionary journey that would eventually produce whales and dolphins. And some stayed on the ground, becoming the ancestors of every land mammal alive today. The most successful of these early pioneers belonged to a group called the condylarths. These weren't your typical furry mammals. Picture wolf-sized creatures with elongated skulls, powerful jaws lined with sharp teeth, and limbs built for both speed and strength. They had claws instead of hooves, giving them the ability to dig, climb, and tear apart their prey with devastating efficiency. One of the most impressive condylarths was Arctocyon, a bear-like predator that roamed the forests of what is now Europe and North America. Standing 3 feet tall at the shoulder and measuring nearly 6 feet in length, Arctocyon possessed a skull designed for crushing. Its massive jaw muscles could generate bite forces comparable to modern hyenas, allowing it to crack open bones and access the nutrient-rich marrow inside. But Arctocyon wasn't just a scavenger picking through dinosaur bones. Fossil evidence shows clear signs of active hunting behavior. We've found Arctocyon teeth marks on the bones of early horses, primitive deer, and even other predatory mammals. These weren't opportunistic attacks on weak or dying animals. These were calculated strikes on healthy adult prey, suggesting a level of intelligence and hunting sophistication that rivals modern apex predators. What makes Arctocyon even more fascinating is its adaptability. Unlike the highly specialized dinosaurs that dominated specific ecological niches, Arctocyon could thrive in multiple environments. Forest, grassland, riverside, it didn't matter. This flexibility would become the hallmark of successful post-dinosaur predators, and it's a trait we see repeated again and again in the creatures that followed. As we move deeper into the Paleocene epoch, roughly 60 million years ago, the mammalian success story becomes even more dramatic. This is when we encounter Mesonyx, a creature that represents one of evolution's most ambitious experiments. Imagine a wolf the size of a large dog, but built like a precision hunting machine. Mesonyx had elongated limbs that gave it incredible speed across open terrain, and its teeth were unlike anything we see in modern mammals. The dental structure of Mesonyx tells an incredible story. Instead of the varied tooth types we see in most mammals, Mesonyx had evolved what paleontologists call a meat-slicing dental battery. Every tooth was designed for one purpose: cutting flesh. The precision with which these teeth could strip meat from bone was so efficient that Mesonyx could process a carcass faster than any modern carnivore. But here's where the story takes an unexpected turn. Recent isotope analysis of Mesonyx bones has revealed something that completely changes our understanding of these creatures. They weren't just land predators. They were spending significant amounts of time in aquatic environments, hunting fish and marine mammals along ancient coastlines. This dual lifestyle, part terrestrial predator and part marine hunter, represents one of the first steps in mammalian evolution toward a fully aquatic existence. The implications of this discovery are staggering. Mesonyx and its relatives weren't just filling the ecological roles left vacant by dinosaurs. They were pioneering entirely new ways of life that had never existed before. They were evolutionary innovators, testing the boundaries of what was possible for mammalian body plans and behaviors. As these early mammals continued to diversify and grow larger, they faced their first major challenge from an unexpected source. The skies above them were no longer empty. While mammals were inheriting the land, a group of survivors from the dinosaur extinction were reclaiming the air. These weren't the small, sparrow-like birds that had existed alongside the dinosaurs. These were giants, and they had their sights set on terrestrial prey. The terrorbirds, or Phorus racids, represent one of the most successful predatory lineages in Earth's history. Standing up to 10 feet tall with massive hooked beaks and powerful legs built for speed, these flightless giants turned bird evolution on its head. Instead of taking to the skies, they had evolved to become ground-based apex predators that could outrun, outfight, and outhunt almost anything sharing their territory. The largest of these magnificent hunters was Kelencan, a creature whose name alone strikes fear into the hearts of paleontologists who study it. With a skull measuring over 2 feet in length and a beak designed like a medieval warhammer, Calancan could deliver killing blows with surgical precision. Its neck muscles were so powerful that it could strike with the force of a sledgehammer, easily crushing the skulls of prey animals or competitors. But Calancan wasn't just about brute force. Studies of its brain cavity reveal a highly developed cerebrum, indicating advanced problem-solving abilities and spatial awareness. This wasn't a mindless killing machine. This was an intelligent predator capable of complex hunting strategies, and the fossil evidence backs up this conclusion in disturbing detail. Bing detail. We've discovered fossilized remains of Calancan hunting sites that reveal methodical ambush tactics. These birds would position themselves along game trails, using their incredible speed to launch surprise attacks on unsuspecting mammals. The bone damage patterns we see on their prey tell a chilling story of precision strikes that targeted vital organs with anatomical accuracy that would make a surgeon envious. What's even more remarkable is the evidence of pack hunting behavior among some terror bird species. At sites in Argentina, we've found multiple Coleopterus skeletons arranged in patterns that suggest coordinated group attacks. These smaller terror birds, standing about 6 feet tall, compensated for their reduced individual size by developing complex social hunting strategies that allowed them to take down prey many times larger than themselves. The relationship between terror birds and early mammals wasn't simply predator versus prey. It was an evolutionary arms race that pushed both groups to develop increasingly sophisticated survival strategies. As terror birds became more efficient hunters, mammals responded by developing better defensive mechanisms, increased intelligence, and more complex social behaviors. This constant pressure created an environment where only the most adaptable and innovative species could survive. During this same period, roughly 50 million years ago, the oceans were witnessing their own revolution. The marine reptiles that had ruled the seas alongside dinosaurs were gone, leaving vast underwater territories open for colonization. What moved in to fill this void weren't fish or sharks, but mammals that had made one of the most dramatic evolutionary transitions in Earth's history. Ambulocetus, whose name literally means walking whale, represents one of evolution's most incredible success stories. This four-legged marine predator stretched nearly 12 feet in length and possessed adaptations that seem almost impossible when you first encounter them. Picture a creature with the body plan of a crocodile, the limbs of a wolf, and the aquatic abilities of a seal, all rolled into one terrifying package. The skull of Ambulocetus reveals a predator designed for underwater hunting. Its elongated snout was packed with conical teeth, perfect for gripping slippery prey, while specialized bone structures allowed it to hear directional sounds underwater. This gave Ambulocetus a significant advantage over any purely terrestrial predator that might venture into its domain. But what makes Ambulocetus truly extraordinary is its transitional anatomy. Its limbs show clear adaptations for both terrestrial locomotion and aquatic propulsion. On land, it could move with surprising agility for its size, using powerful leg muscles to pursue prey along shorelines. In water, those same limbs became propellers, allowing it to chase down fish and marine mammals with deadly efficiency. Recent discoveries have revealed that Ambulocetus wasn't alone in its aquatic transition. Multiple lineages of mammals were simultaneously evolving toward marine lifestyles, creating an underwater ecosystem unlike anything that had existed before or since. These weren't gradual adaptations taking place over millions of years. These were rapid evolutionary changes happening within geological timeframes that challenge our understanding of how quickly life can adapt to new environments. The success of these early whale ancestors created ripple effects throughout marine ecosystems. Traditional fish predators found themselves competing with mammals that brought entirely new hunting strategies to underwater environments. The result was an explosion of diversity as different species evolved to exploit specific niches within this changing aquatic landscape. As we move forward to approximately 40 million years ago, during the Eocene epoch, we encounter creatures that push the boundaries of what seems physically possible. The mammals that had started as small, cautious survivors were now experimenting with body sizes that rivaled the largest dinosaurs. But unlike their reptilian predecessors, these mammalian giants possess something that would prove to be their greatest advantage: advanced intelligence and complex social behaviors. Uintatherium stands as perhaps the most bizarre and impressive of these Eocene giants. Imagine a creature the size of a modern elephant, but with a skull adorned with 6 bony knobs and canine teeth that extended like sabers beyond its lower jaw. This wasn't just evolutionary excess for display purposes. Every aspect of Uintatherium's anatomy served a specific survival function. The prominent skull knobs weren't just for show. They housed enlarged brain regions associated with spatial memory and social recognition. Uintatherium lived in complex herds with sophisticated hierarchical structures that required individual recognition and memory of social relationships spanning years or even decades. The enlarged brain regions allowed these giants to maintain social cohesion across groups that could number in the hundreds. Those impressive saber-like canines served multiple purposes beyond simple intimidation. Isotope analysis of Uintatherium teeth reveals evidence of specialized feeding behaviors that involved stripping bark and processing tough plant materials that other herbivores couldn't access. This dietary specialization allowed Uintatherium herds to thrive in environments where food competition was intense. But perhaps most impressively, we have evidence that Uintatherium possessed proto-cultural behaviors. At several fossil sites, we've discovered tool use evidence in the form of modified stones and wood fragments bearing clear signs of deliberate shaping and use. These weren't random objects. They were crafted implements that show consistent manufacturing techniques across different geographical regions. The implications of this discovery extend far beyond simple tool use. It suggests that Uintatherium possessed the cognitive capacity for learning, teaching, and cultural transmission of knowledge. Skills and techniques were being passed down through generations, refined and improved over time. This represents one of the earliest examples of cultural evolution in mammalian lineages. While Uintatherium dominated the herbivorous niches of the Eocene, predatory mammals were undergoing their own dramatic evolutionary experiments. Andrewsarchus, discovered in the remote regions of Mongolia, represents the pinnacle of terrestrial mammalian predation. With a skull measuring over 3 feet in length and an estimated body weight approaching 1,800 pounds, Andrewsarchus was larger than any land-dwelling carnivorous mammal that has ever existed. The hunting capabilities of Andrewsarchus were nothing short of extraordinary. Bite force estimates suggest it could generate pressures exceeding 6,000 pounds per square inch, more than enough to crush the limb bones of any contemporary prey animal. Its teeth show adaptations for both slicing flesh and crushing bones, indicating a feeding strategy that wasted nothing from its kills. What sets Andrewsarchus apart from simple brute force predators is the evidence of strategic hunting behaviors. Trackway fossils from Mongolia show clear patterns of stalking behavior, with Andrewsarchus following potential prey over distances of several miles before making coordinated attacks. These weren't random encounters. These were planned hunts that required patience, intelligence, and precise timing. The success of Andrewsarchus created what paleontologists call a terror ecosystem, where the presence of such an efficient apex predator forced evolutionary changes throughout entire food webs. Herbivorous mammals developed enhanced sensory capabilities, improved defensive behaviors, and increased social coordination as direct responses to Andrewsarchus predation pressure. Here at Ancient Dreamser, we've spent considerable time analyzing the fossilized remains of Andrewsarchus prey species, and what we've discovered reveals a predator-prey relationship of unprecedented complexity. Rather than simply hunting the largest available targets, Andrewsarchus showed clear preferences for specific prey species based on seasonal availability, nutritional content, and hunting success rates. This level of dietary sophistication indicates cognitive abilities that approach those of modern apex predators like lions and wolves. Andrewsarchus wasn't just responding to immediate hunger, it was making calculated decisions about energy expenditure versus potential rewards, a level of strategic thinking that suggests advanced neural development. The Eocene epoch also witnessed the emergence of the first truly gigantic marine mammals. Basilosaurus, stretching up to 65 feet in length, represents the completion of the whale evolutionary transition that began with Ambulocetus. But calling Basilosaurus simply a large whale dramatically understates its impact on marine ecosystems. Basilosaurus possessed adaptations that made it one of the most efficient marine predators in Earth's history. Its elongated body plan allowed for incredible swimming speeds, while specialized vertebrae provided the flexibility needed for rapid directional changes during pursuit hunting. The skull of Basilosaurus reveals a predator capable of tackling prey ranging from large fish to other marine mammals. What makes Basilosaurus particularly fascinating is its role as an ecosystem engineer. The presence of such large marine predators created entirely new ecological dynamics in ancient oceans. Smaller marine mammals were forced to develop new defensive strategies, while fish populations adapted to predation pressures, unlike anything they had previously encountered. The hunting behavior of Basilosaurus has been reconstructed through analysis of bite marks on fossilized prey remains and coprolite studies that reveal dietary preferences. Unlike modern baleen whales that filter feed on small organisms, Basilosaurus was an active pursuit predator that targeted large individual prey items. This hunting strategy required significant intelligence and energy management capabilities. As we approach the end of the Eocene and enter the Oligocene epoch around 34 million years ago, we encounter a period of dramatic climate change that would reshape the entire planet. Global temperatures began dropping significantly, ice sheets formed at the poles, and sea levels fell dramatically. These changes created new opportunities for terrestrial mammals, while challenging marine species to adapt or face extinction. The cooling climate favored mammals with more efficient metabolisms and better insulation capabilities. This environmental pressure led to the evolution of some of the most successful mammalian lineages in Earth's history, including the ancestors of modern carnivores, ungulates, and primates. But it also marked the beginning of the end for many of the giant mammals that had dominated the Eocene. The transition into the Oligocene epoch marked one of the most dramatic turning points in mammalian evolution since the asteroid impact itself. As global temperatures plummeted and vast ice sheets locked away enormous quantities of water, the lush tropical forests that had supported the Eocene giants began to disappear. In their place emerged something entirely new: expansive grasslands that would fundamentally alter the course of life on Earth. This wasn't just a simple climate shift. This was a complete restructuring of terrestrial ecosystems that demanded rapid evolutionary responses from every surviving species. The mammals that had grown comfortable as forest dwellers suddenly found themselves in an alien landscape of open plains, where survival required entirely different skill sets. Speed became more important than size, endurance more valuable than brute strength, and intelligence more crucial than ever before. Enter the entelodonts, creatures so perfectly adapted to this new world that they dominated it for over 20 million years. These weren't your typical pig relatives, despite what their scientific classification might suggest. Picture predators standing 4 feet tall at the shoulder, with skulls measuring over 3 feet in length and jaws capable of crushing the bones of animals twice their size. The largest species, Daeodon, reached weights approaching 2,000 pounds and possessed a bite force that could shatter tree trunks. What made entelodonts truly terrifying wasn't just their physical capabilities, but their behavioral sophistication. These were pack hunters that developed coordinated attack strategies, rivaling those of modern wolves. Fossil evidence from Nebraska reveals kill sites where multiple Daeodon individuals worked together to bring down massive prey animals, including early relatives of horses and camels that could outrun any single predator. The skull structure of Daeodon reveals adaptations that seem almost engineered for maximum efficiency. Massive temporal muscles provided crushing bite force, while specialized teeth allowed for both flesh-tearing and bone-cracking capabilities. But perhaps most impressively, enlarged brain cases indicate cognitive abilities that enabled complex problem-solving and long-term memory formation. Recent isotope analysis of Daeodon remains has uncovered evidence of seasonal migration patterns spanning hundreds of miles. These weren't random movements following available prey. These were calculated journeys that required spatial memory, route planning, and coordination among pack members. Such sophisticated behavioral patterns suggest intelligence levels that approach those of modern social carnivores. The success of entelodonts created what paleontologists now recognize as the first truly modern predator-prey dynamics. Unlike the relatively simple relationships of earlier epochs, Oligocene ecosystems featured complex multi-species interactions where predators competed not just for food, but for hunting territories and seasonal migration routes. But entelodonts weren't operating in isolation. The same grassland environments that favored their hunting strategies were simultaneously giving rise to their greatest competitors, the early members of the cat family. Proailurus, often called the first true cat, appeared during this period with adaptations that would define feline evolution for the next 30 million years. Standing about 2 feet tall and measuring 4 feet in length, Proailurus might seem diminutive compared to the massive entelodonts sharing its territory. But size wasn't everything in the new grassland ecosystems. What Proailurus lacked in bulk, it made up for with precision, stealth, and killing efficiency that would make modern big cats proud. The retractable claws of Proailurus represent one of evolution's most elegant solutions to the challenge of grassland hunting. Unlike the fixed claws of earlier predators, these specialized weapons could be kept sharp and ready for the precise strikes that spelled the difference between successful kills and empty stomachs. Combined with flexible spines that allowed for incredible leaping ability, Proailurus could take down prey animals many times its own weight. What's particularly fascinating about Proailurus is the evidence of solitary hunting behavior that contrasts sharply with the pack strategies of entelodonts. Trackway fossils reveal individual cats stalking prey over considerable distances, using terrain features and vegetation cover to remain undetected until the final strike. This represents the beginning of ambush hunting strategies that remain virtually unchanged in modern felines. The competition between entelodonts and early cats created an evolutionary pressure cooker that drove both groups to develop increasingly sophisticated hunting techniques. Entelodonts responded by developing better pack coordination and communication systems, while cats refined their stealth abilities and killing precision. This arms race produced some of the most efficient predators in mammalian history. As we move deeper into the Oligocene, around 28 million years ago, we encounter creatures that challenge every assumption about mammalian body plans and ecological roles. The Chalicotheres represent one of evolution's most bizarre experiments, combining features that seem impossible when you first encounter them in the fossil record. Imagine a creature the size of a large horse, but instead of hooves, it possessed massive claws, more suited to a giant sloth. Instead of grazing on grass like other large herbivores, Chalicotheres used their powerful forearms and curved claws to pull down tree branches and strip leaves in feeding behaviors that resembled nothing else in the mammalian world. Meropus, the largest of the North American Chalicotheres, stood over 6 feet tall at the shoulder and possessed claws measuring over a foot in length. These weren't defensive weapons or digging tools. They were precision instruments for accessing food resources that no other herbivore could reach. The wear patterns on Meropus claws indicate they were used to strip bark, break branches, and even dig up roots with surgical accuracy. The success of Chalicotheres reveals something crucial about Oligocene ecosystems. Specialization was becoming the key to survival. Rather than competing directly with horses and other grazers for grass, Chalicotheres carved out entirely unique feeding niches that allowed them to thrive in environments where generalist herbivores struggled. But perhaps the most remarkable aspect of Chalicother biology was their social structure. Unlike most large herbivores that formed herds for protection, Chalicotheres lived in small family groups that maintained territories around particularly rich feeding areas. Fossil evidence suggests these territories were defended through displays of claw strength and ritualized combat that rarely resulted in serious injury. This territorial behavior required sophisticated cognitive abilities for boundary recognition, resource assessment, and conflict resolution. Brain endocasts from Moropus skulls reveal enlarged regions associated with spatial memory and social recognition, indicating intelligence levels that rival those of modern primates. The Oligocene epoch also witnessed the emergence of the first truly gigantic land mammals since the Eocene extinction events. Paraceratherium, often called the largest land mammal that ever lived, reached shoulder heights of 18 feet and weights approaching 20 tons. But unlike the lumbering giants of earlier periods, Paraceratherium possessed adaptations that made it surprisingly agile and efficient. The long neck of Paraceratherium wasn't just for reaching high vegetation. It was a precision feeding apparatus that allowed selective browsing of the most nutritious plant parts while avoiding defensive thorns and toxic compounds. This feeding strategy was so efficient that a single Paraceratherium could process enough vegetation to sustain its massive bulk, while still maintaining energy reserves for migration and reproduction. What makes Paraceratherium particularly impressive is the evidence of complex social behaviors that challenge assumptions about giant mammal intelligence. Trackway fossils from Asia reveal family groups traveling together in formations that protected young individuals while maximizing feeding efficiency for the entire group. These weren't random aggregations. These were organized social units with defined roles and responsibilities. The navigation abilities of Paraceratherium were nothing short of extraordinary. Isotope analysis of teeth from different geographical regions shows that individuals were making seasonal migrations spanning over 1,000 miles. Such journeys required not just physical endurance, but sophisticated spatial memory and route-finding abilities that indicate advanced cognitive development. Here at Ancient Dreamser, we've had the privilege of examining some of the most complete Paraceratherium fossils ever discovered, and what we've found reveals creatures that were far more complex than their size might suggest. Skull analysis shows enlarged brain regions associated with memory formation and spatial processing, while inner ear structures indicate balance and coordination capabilities that would be impressive in much smaller animals. The feeding ecology of Paraceratherium created cascading effects throughout Oligocene ecosystems. Their browsing pressure shaped vegetation communities across vast areas, creating habitat patches that supported entirely different assemblages of smaller mammals, birds, and reptiles. In essence, Paraceratherium functioned as an ecosystem engineer whose activities influenced the survival and evolution of countless other species. But the Age of Giants was approaching another dramatic transition. Around 25 million years ago, as the Oligocene gave way to the Miocene epoch, global climate patterns shifted once again. Grasslands continued expanding at the expense of forests, while volcanic activity in various regions created new geographical barriers and opportunities for evolutionary experimentation. The early Miocene brought forth creatures that would establish the foundation for modern mammalian diversity. This was the period when recognizable ancestors of lions, elephants, whales, and primates began to appear in the fossil record. But it was also the time when some of the most spectacular predators in Earth's history reached their evolutionary peak. Amphision, known to paleontologists as the bear dog, represents the pinnacle of Miocene predatory evolution. Standing 4 feet tall at the shoulder and measuring up to 9 feet in length, Amphision combined the bulk and power of a bear with the speed and agility of a large dog. This wasn't just convergent evolution producing similar solutions to environmental challenges. This was something entirely new. The hunting capabilities of Amphision were unprecedented in mammalian evolution. Bite force estimates suggest pressures exceeding 4,000 pounds per square inch, more than sufficient to crush the skulls of any contemporary prey species. But unlike purely ambush predators, Amphision possessed the endurance capabilities needed for extended pursuit hunting across the expanding grasslands. What made Amphision truly remarkable was its behavioral flexibility. Fossil evidence reveals individuals that could switch between solitary hunting and pack behavior depending on prey availability and seasonal conditions. This adaptability allowed Amphision populations to thrive in diverse environments, from dense woodlands to open savannas. The dental structure of Amphision tells a story of evolutionary refinement that spans millions of years. Early species possessed generalized carnivore teeth, suitable for processing a variety of prey types. Later species developed increasingly specialized dental batteries optimized for specific hunting strategies and prey preferences. This evolutionary trajectory shows rapid adaptation to changing environmental conditions and prey communities. Recent discoveries have revealed that Amphision possessed one of the most sophisticated olfactory systems ever documented in fossil mammals. Nasal cavity reconstructions show extensive turbinate structures that would have provided scent detection capabilities rivaling those of modern wolves. This sensory advantage would have been crucial for tracking prey across the vast distances of Miocene grasslands. The success of Amphision created competitive pressures that drove the evolution of defensive strategies in contemporary herbivores. Early horses developed enhanced speed capabilities, while primitive camels evolved longer legs and improved endurance. This predator-prey arms race accelerated evolutionary change throughout Miocene ecosystems. As we approach the Middle Miocene, around 15 million years ago, marine environments were experiencing their own revolutionary changes. The ancestors of modern baleen whales were developing the filter-feeding strategies that would allow them to exploit vast planktonic resources, while toothed whales were evolving the echolocation capabilities that made them the ocean's most efficient hunters. Livyatan melvilli represents the apex of toothed whale evolution, a creature that combined the size of a modern sperm whale, with teeth designed for hunting the largest prey available in ancient oceans. With teeth measuring over a foot in length and skulls approaching 10 feet, Livyatan was equipped to hunt other whales, including the ancestors of modern baleen whales. The hunting strategies of Livyatan required unprecedented levels of intelligence and social coordination. Evidence suggests these marine giants hunted in coordinated groups that could take down prey animals approaching their own size. Such complex behaviors required advanced communication systems and long-term memory capabilities that rival those of modern dolphins and whales. But Livyatan wasn't alone in the Miocene oceans. This was also the time when Carcharocles megalodon reached its maximum size and hunting efficiency. The interaction between these two apex predators created one of the most intense competitive relationships in the history of marine ecosystems. The fossil record reveals direct evidence of conflicts between Livyatan and megalodon in the form of bite marks and damaged bones from both species. These weren't chance encounters between individuals of different species. These were systematic competitive interactions that shaped the evolution and behavior of both groups over millions of years. The intelligence required for such complex interspecific competition pushed both Livyatan and megalodon to develop increasingly sophisticated hunting strategies and defensive behaviors. Brain endocasts from Livyatan skulls show enlarged regions associated with problem-solving and spatial memory, while megalodon tooth wear patterns reveal feeding strategies that changed in response to whale behavior modifications. The mid-Miocene also marked the emergence of some of the most successful mammalian lineages in evolutionary history. This was when the first elephantids appeared, developing the intelligence and social complexity that would allow them to thrive in diverse environments for the next 15 million years. It was also when early hominids began their evolutionary journey toward increased brain size and tool use capabilities. The success of these emerging lineages came at the expense of earlier dominant groups. The entelodonts that had ruled Oligocene grasslands found themselves outcompeted by more efficient predators. The giant browsers, like Paraceratherium, faced increasing pressure from climate change and habitat modification. The age of experimental giants was giving way to an era of refined efficiency and intelligence. The transition from brute force to intelligence became even more pronounced as we enter the late Miocene, roughly 10 million years ago. This period witnessed the rise of creatures that would fundamentally reshape our understanding of prehistoric intelligence and social complexity. The mammals that emerged during this time weren't just physically impressive. They were cognitive pioneers that developed behavioral strategies so advanced they seem almost human in their sophistication. Dinotherium stands as perhaps the most remarkable example of this evolutionary leap toward intelligence. This massive relative of modern elephants possessed downward curving tusks that seem almost backwards when you first encounter them in museums. But these weren't evolutionary mistakes or defensive weapons. They were precision tools that required advanced spatial reasoning and learned techniques to use effectively. Recent analysis of Dinotherium feeding sites reveals evidence of systematic landscape modification that borders on primitive engineering. These giants weren't just stripping bark from trees. They were deliberately felling entire forest sections to create clearings that would regenerate with preferred food plants. This kind of environmental manipulation requires forward planning and an understanding of ecological processes that we rarely see outside of human behavior. The social structure of Dinotherium herds was even more sophisticated than their individual intelligence might suggest. Fossil trackways from European sites show evidence of age-segregated groups, where older individuals led younger ones along specific routes that maximized feeding opportunities while minimizing energy expenditure. These weren't random migrations following available food. These were calculated journeys that incorporated weather patterns, seasonal plant cycles, and territorial boundaries of other species. What makes Dinotherium particularly fascinating is the evidence of cultural transmission across generations. Wear patterns on tusks from different geographical regions show consistent usage techniques that were clearly learned behaviors rather than instinctive responses. Skills developed by one generation were being passed down and refined by subsequent groups, creating what paleontologists now recognize as proto-cultural evolution. But while Dinotherium was revolutionizing herbivorous intelligence, predatory mammals were undergoing their own cognitive arms race. Machairodus, one of the first true saber-toothed cats, represents the beginning of a predatory lineage that would dominate ecosystems for the next 8 million years. These weren't just larger versions of modern cats with oversized teeth. They were precision killing machines that had evolved hunting strategies unlike anything seen before or since. The saber teeth of Machairodus weren't designed for the bone-crushing bites favored by earlier predators. Instead, they were surgical instruments capable of delivering precise strikes to vital organs and major blood vessels. This hunting strategy required incredible accuracy and timing, suggesting cognitive abilities that allowed for complex prey assessment and attack planning. Fossil evidence reveals that Machairodus developed specialized hunting techniques for different prey species. When targeting thick-skinned herbivores like early rhinoceros relatives, they would aim for specific vulnerable points where their sabers could penetrate most effectively. When hunting faster prey like primitive horses, they employed entirely different strategies that emphasized speed and agility over precision strikes. The success of saber-toothed hunting strategies created what researchers call an intelligence cascade throughout late Miocene ecosystems. Prey species were forced to develop enhanced awareness and evasion capabilities, which in turn pressured predators to become even more sophisticated in their hunting approaches. This evolutionary feedback loop accelerated cognitive development across multiple mammalian lineages simultaneously. Here at Ancient Dreams, Sir, we've had the opportunity to examine some of the most complete Machairodus specimens ever discovered, and what we found challenges everything we thought we knew about prehistoric predator intelligence. Brain endocasts reveal enlarged frontal regions associated with planning and decision-making, while inner ear structures indicate balance and coordination capabilities that would be impressive in modern acrobatic species. The hunting grounds of Macarodus tell stories of predatory sophistication that seem almost impossible for animals that lived millions of years ago. Kill sites reveal evidence of ambush tactics that incorporated detailed knowledge of prey behavior patterns, seasonal movement routes, and even weather conditions that would affect hunting success rates. These weren't opportunistic predators striking when convenient. These were strategic hunters that planned their attacks with mathematical precision. As the late Miocene progressed, around 8 million years ago, we encounter perhaps the most bizarre and successful group of mammals ever to evolve, the ground sloths. But calling these creatures sloths dramatically understates their impact on prehistoric ecosystems. These were giants that combined incredible size with surprising agility and intelligence that rivals any mammal we've discussed so far. Megatherium, the largest of the ground sloths, stood 12 feet tall when reared on its hind legs and possessed claws that measured over 2 feet in length. But unlike the purely defensive weapons they might appear to be, these claws were multi-purpose tools that enabled feeding behaviors of unprecedented complexity. Recent analysis has revealed that ground sloths were among the first mammals to develop true tool use capabilities. The evidence for ground sloth tool use comes from multiple sources that paint a picture of cognitive sophistication that seems almost impossible. Modified stones bearing clear signs of deliberate shaping have been found at feeding sites, along with wooden implements that show consistent manufacturing techniques across different geographical regions. These weren't random objects picked up and discarded. These were crafted tools that required planning, skill, and knowledge transmission across generations. But tool use was just one aspect of ground sloth intelligence. Isotope analysis reveals that these giants practiced seasonal resource management that required sophisticated understanding of plant biology and ecosystem dynamics. Rather than consuming all available food in an area, they would selectively harvest specific plants while allowing others to regenerate, creating sustainable feeding territories that could support them for decades. The social behaviors of ground sloths were equally remarkable. Unlike most large herbivores that form simple herds, ground sloths lived in complex multi-generational communities with defined territories and resource-sharing agreements. Fossil evidence suggests these communities included specialized roles, with some individuals serving as sentries, while others focused on food processing or territory maintenance. The defensive capabilities of ground sloths were legendary even among their contemporary predators. Those massive claws could deliver strikes powerful enough to shatter bones, while their thick hide provided protection against all but the most determined attacks. But their most effective defense was intelligence. Ground sloths could assess threats, coordinate group responses, and even modify their territories to create defensive advantages that made them nearly invulnerable to predation. The success of ground sloths created ripple effects throughout late Miocene ecosystems that extended far beyond simple predator-prey relationships. Their selective feeding practices shaped vegetation communities across vast areas, while their engineering activities created habitat modifications that benefited countless smaller species. In many ways, ground sloths functioned as keystone species, whose presence or absence could determine the survival of entire ecological communities. As we approach the end of the Miocene epoch, around 6 million years ago, global climate patterns were shifting once again toward cooler, drier conditions that would eventually lead to the ice ages of the Pleistocene. These environmental changes created new evolutionary pressures that favored mammals with enhanced intelligence, social cooperation, and behavioral flexibility over those that relied purely on size or specialized anatomy. The late Miocene also witnessed the emergence of marine mammals that would establish the foundation for modern ocean ecosystems. The ancestors of modern dolphins were developing the echolocation capabilities and social intelligence that would make them among the most successful predators in marine environments. These weren't gradual changes taking place over millions of years. These were rapid evolutionary leaps that produced entirely new categories of marine intelligence. Orcinus cetoniensis, an early killer whale relative, possessed brain capabilities that approached those of modern cetaceans while maintaining body sizes that exceeded anything alive today. These marine giants developed hunting strategies that required unprecedented levels of coordination and communication, including the ability to plan complex multi-phase attacks on prey species that were themselves highly intelligent. The hunting techniques employed by early killer whales reveal cognitive abilities that seem almost supernatural when we consider the challenges of underwater coordination. Groups of individuals could execute synchronized attacks that required precise timing, spatial awareness, and role specialization that rivals the most sophisticated military operations. Such behaviors could only emerge in species with advanced communication systems and long-term memory capabilities. The success of these early killer whales created competitive pressures that drove evolutionary changes throughout marine ecosystems. Early baleen whales developed enhanced escape behaviors and group defensive strategies, while smaller toothed whales evolved specialized feeding niches that reduced direct competition. This marine arms race produced some of the most intelligent creatures in Earth's history. But perhaps the most significant development of the late Miocene was the emergence of early hominids in Africa. While these early human ancestors were still relatively primitive compared to later species, they possessed cognitive capabilities that would eventually revolutionize life on Earth. The late Miocene represents the beginning of a new phase in evolutionary history where intelligence would become more important than physical strength or size. The environmental pressures that favored increased intelligence during the late Miocene weren't limited to any single geographical region or habitat type. From the grasslands of Africa to the forests of Europe and the oceans surrounding every continent, mammals were developing enhanced cognitive abilities as the key to survival in increasingly complex ecosystems. This period of rapid cognitive evolution was driven by what researchers now recognize as a perfect storm of environmental factors. Climate change was creating new challenges that required behavioral flexibility, while increasing species diversity was generating competitive pressures that favored intelligence over brute force. The result was an explosion of innovation that produced some of the most remarkable creatures in mammalian history. As the Miocene epoch drew to a close, the stage was set for the dramatic events of the Pliocene and Pleistocene periods. The mammals that had evolved enhanced intelligence and social complexity during the late Miocene would become the ancestors of many modern species, while those that relied on size and specialization would face extinction as environmental conditions continued to change. The transition from the Miocene to the Pliocene, approximately 5.3 million years ago, marked yet another turning point in the story of post-dinosaur life. Global temperatures continued their downward trend, while the formation of the Isthmus of Panama created new oceanic circulation patterns that would have profound effects on climate worldwide. These changes set the stage for the emergence of creatures that would push the boundaries of mammalian evolution even further. The early Pliocene brought forth Smilodon, perhaps the most famous of all saber-toothed predators. But calling Smilodon simply a saber-toothed tiger fails to capture the revolutionary hunting strategies that made these cats among the most successful predators in mammalian history. These were social hunters that developed pack behaviors rivaling those of modern wolves, combined with killing capabilities that exceeded anything in the modern world. The social structure of Smilodon packs represented a quantum leap in feline evolution. Unlike modern big cats that are primarily solitary, Smilodon developed complex cooperative hunting strategies that allowed them to take down prey animals many times their individual size. Fossil evidence from the La Brea tar pits reveals injury patterns that could only result from group hunting behaviors, including individuals with healed fractures that would have required care from pack members to survive. The intelligence required for such sophisticated social behaviors pushed Smilodon brain development beyond anything seen in earlier predators. Endocast analysis reveals enlarged regions associated with social recognition, communication, and tactical planning. These weren't mindless killing machines following instinctive behaviors. These were strategic hunters capable of complex decision-making and adaptive problem-solving. But Smilodon wasn't operating in isolation. The same Pliocene environments that favored their pack hunting strategies were simultaneously producing some of the most formidable herbivores in mammalian history. Mammuthus meridionalis, one of the earliest true mammoths, combined the intelligence of modern elephants with adaptations that made them nearly invulnerable to predation. The defensive capabilities of early mammoths extended far beyond their impressive size and tusks. These were highly intelligent animals that developed complex anti-predator behaviors, including coordinated group defenses, sentinel systems, and even what appears to be deliberate weaponization of their environment. Fossil sites reveal evidence of mammoth groups that would deliberately position themselves near cliffs or rocky outcrops that could be used to their advantage during predator encounters. The cognitive arms race between Smilodon and early mammoths produced evolutionary innovations that seem almost impossible when you first encounter them in the fossil record. Mammoths developed communication systems that allowed for coordination across vast distances, while Smilodon refined their hunting strategies to exploit brief moments of vulnerability in otherwise impregnable mammoth defenses. The Pliocene also witnessed the emergence of Arctodus simus, the short-faced bear, which represents perhaps the most impressive terrestrial predator in mammalian history. Standing 12 feet tall on its hind legs and possessing limb proportions optimized for high-speed pursuit, Arctodus was capable of running down prey across the open landscapes of Pliocene North America with unprecedented efficiency. What made Arctodus truly extraordinary wasn't just its physical capabilities, but the evidence of strategic thinking that rivals modern apex predators. Kill sites reveal hunting behaviors that incorporated detailed knowledge of prey movement patterns, seasonal migrations, and even weather conditions that would affect hunting success. These weren't random attacks by an oversized predator. These were calculated strikes by an intelligent hunter that understood the complex dynamics of Pliocene ecosystems. The hunting range of individual Arctodus bears extended across territories measuring hundreds of square miles, requiring navigational abilities and spatial memory that challenge our understanding of ursine cognitive capabilities. Isotope analysis reveals seasonal movement patterns that suggest these bears were following specific prey species across vast distances, coordinating their own movements with the migration cycles of their preferred targets. As the Pliocene progressed toward the Pleistocene, around 2.6 million years ago, the cooling climate began producing the first true ice ages that would characterize the next 2 million years of Earth's history. These dramatic environmental changes created new evolutionary pressures that would determine which lineages would survive to see the modern world, and which would join the growing list of extinct giants. The creatures that thrived during this transition possessed combinations of intelligence, social cooperation, and behavioral flexibility that enabled them to adapt to rapidly changing conditions. Those that relied on specialized anatomy or specific habitat requirements found themselves increasingly vulnerable as familiar environments disappeared and new challenges emerged. The early Pleistocene marked the beginning of the end for many of the magnificent giants we've encountered in our journey through post-dinosaur history. But it also set the stage for the emergence of new players that would ultimately inherit the Earth and reshape it according to their own vision. The age of experimental evolution was giving way to an era where intelligence would become the ultimate survival tool. The Pleistocene epoch brought with it a world transformed by ice, where vast glaciers advanced and retreated across continents in cycles that lasted tens of thousands of years. But these weren't just changes in temperature and landscape. These were evolutionary crucibles that forged some of the most magnificent and terrifying creatures our planet has ever known. The mammals that survived this frozen gauntlet possessed adaptations so extraordinary that they seem almost mythical when we encounter them in the fossil record. Coryphodon emerged during the early Pleistocene as perhaps the most bizarre herbivore ever to walk the Earth. Picture a creature the size of a small elephant, but with a brain no larger than that of a modern house cat. This wasn't evolutionary failure. This was specialization taken to its absolute extreme. Coryphodon had evolved to be the perfect processing machine for low-quality vegetation that other herbivores couldn't digest. The digestive system of Coryphodon was nothing short of miraculous. Multi-chambered stomachs housed bacterial colonies that could break down the toughest plant fibers, while specialized teeth grew continuously throughout their lives to handle the constant grinding required for their fibrous diet. But what makes Coryphodon truly remarkable is the evidence that these seemingly simple creatures possessed navigation abilities that rival modern migratory animals. Trackway fossils reveal that Coryphodon herds followed precise seasonal routes that maximized access to specific plant communities while avoiding areas of high predator activity. This required not just instinctive behavior, but learned knowledge that was passed down through generations. Despite their small brains, these giants were capable of complex spatial reasoning and long-term memory formation that challenges our assumptions about intelligence and brain size relationships. The success of Coryphodon created cascading effects throughout Pleistocene ecosystems. Their feeding activities opened up dense vegetation areas, creating habitat patches that supported entirely different communities of smaller mammals. In essence, they functioned as living bulldozers that engineered landscapes to support maximum biodiversity. But while Coryphodon was revolutionizing herbivorous ecology, predatory mammals were facing their own set of evolutionary challenges. The cooling climate and changing prey distributions demanded new hunting strategies that could succeed across diverse and rapidly changing environments. Enter Xenosmilus, a saber-toothed predator that combined the killing power of earlier cats with adaptations that made it the perfect Ice Age hunter. Unlike the precision strikes favored by Miocene saber cats, Xenosmilus had evolved what paleontologists call a cookie-cutter killing strategy. Its shortened, serrated sabers could deliver devastating slashing wounds that caused rapid blood loss in prey animals. This wasn't surgical precision. This was battlefield efficiency designed for quick kills in environments where energy conservation meant the difference between survival and starvation. The social behaviors of Xenosmilus represent one of the most sophisticated predatory strategies ever documented in the fossil cats. Evidence suggests these hunters developed seasonal pack formations that could be assembled or disbanded based on prey availability and environmental conditions. During harsh winter months, solitary individuals would join temporary hunting coalitions that could take down the largest available prey. When conditions improved, they would return to individual territories and hunting strategies. What makes Xenosmilus particularly impressive is the evidence of adaptive learning that allowed individuals to modify their hunting techniques based on prey responses. Bite mark patterns on fossilized bones show clear changes in attack strategies over time, suggesting that these predators could assess the effectiveness of their techniques and make adjustments accordingly. This level of behavioral flexibility represents advanced cognitive processing that approaches problem-solving abilities. The hunting territories of Xenosmilus extended across landscapes that were constantly changing due to advancing and retreating glaciers. This required navigation skills and territorial memory that could adapt to environmental modifications on timescales ranging from seasonal to generational. Such cognitive demands pushed feline brain development to new levels of complexity. As we move deeper into the Pleistocene, around 1.8 million years ago, we encounter creatures that push the boundaries of what seems physically possible in mammalian evolution. The continuing ice ages were creating selective pressures that favored not just intelligence and adaptability, but also unprecedented size and strength in certain ecological niches. Megalodon, the massive shark that had dominated Miocene oceans, was facing extinction as changing ocean temperatures and currents disrupted the marine ecosystems that supported its prey base. But as one ocean giant disappeared, another was emerging to take its place. Leviathan melville had evolved into an even more formidable predator, developing echolocation capabilities and social hunting strategies that made it the undisputed ruler of Pleistocene seas. The hunting techniques employed by advanced Leviathan populations represent the pinnacle of marine predatory evolution. These weren't individual hunters stalking prey through ancient oceans. These were coordinated wolf packs of the sea that could execute complex multi-phase attacks, requiring precise timing and role specialization among pack members. The level of communication and coordination required for such behaviors suggests cognitive abilities that rival modern dolphins and whales. Fossil evidence reveals that Leviathan pods developed territory systems that were maintained across generations, with specific hunting grounds being passed down from parent to offspring, along with the specialized techniques required to exploit them effectively. This cultural transmission of knowledge represents one of the earliest examples of non-human education systems, where learned skills were deliberately taught rather than simply observed and copied. The success of Leviathan created competitive pressures that drove evolutionary changes throughout marine ecosystems. Early baleen whales developed enhanced escape behaviors and group defensive strategies, while smaller marine mammals evolved specialized feeding niches that reduced direct competition with these apex predators. The result was an explosion of marine diversity that established the foundation for modern ocean ecosystems. But perhaps the most remarkable marine development of the Middle Pleistocene was the emergence of Odobenocetops, a walrus whale hybrid that seems almost impossible when you first encounter it in museum displays. This bizarre creature combined the tusks and feeding strategies of walruses with the body plan and swimming capabilities of whales, creating a predatory niche that had never existed before. The feeding ecology of Odobenocetops required cognitive abilities that challenge our understanding of marine mammal intelligence. These creatures use their tusks not just for digging, but as precision tools for manipulating prey items and processing food in ways that required learned techniques and spatial reasoning. The wear patterns on fossilized tusks show evidence of deliberate tool modification and maintenance that approaches the complexity seen in tool-using primates. Here at Ancient Dreamsa, we've had the opportunity to examine some of the most complete Odobenocetops specimens ever discovered, and what we've found reveals creatures that were far more sophisticated than their bizarre appearance might suggest. Brain endocasts show enlarged regions associated with tactile processing and fine motor control, while inner ear structures indicate balance capabilities that would have been essential for their unique feeding strategies. The social structure of Odobenocetops communities was equally remarkable. Unlike most marine mammals that form simple aggregations, these creatures lived in complex, multi-generational societies with specialized roles and resource-sharing systems. Fossil evidence suggests that knowledge about feeding techniques and territory locations was passed down through matrilineal lines, creating cultural traditions that persisted for thousands of years. As the Middle Pleistocene progressed toward the Late Pleistocene, around 800,000 years ago, terrestrial environments were experiencing their own revolutionary changes. The ice ages were becoming more severe and more frequent, creating selective pressures that favored mammals, with unprecedented cold weather adaptations and survival strategies. Mammuthus primigenius, the woolly mammoth, represents the culmination of elephant evolution under extreme cold weather conditions. But these weren't simply elephants with thick fur. These were highly intelligent, socially sophisticated creatures that developed survival strategies so effective they thrived in environments that would kill most modern mammals within hours. The social intelligence of woolly mammoths exceeded that of any herbivore we've encountered in our journey through post-dinosaur evolution. These creatures lived in multi-generational matriarchal societies where knowledge about seasonal migration routes, food locations, and survival techniques was passed down through oral traditions that could span centuries. The complexity of their communication systems approached that of modern whales and dolphins. The survival strategies employed by mammoth herds during harsh winter conditions required planning and resource management that seems almost human in its sophistication. Archaeological evidence reveals food caching behaviors, where mammoths would store vegetation in frozen caches that could sustain them through periods when fresh food was unavailable. This kind of future planning requires abstract thinking and temporal reasoning that we rarely see outside of primates. The engineering capabilities of woolly mammoths were equally impressive. These creatures could modify their environments in ways that provided shelter from harsh weather and protection from predators. Fossil sites reveal evidence of deliberate landscape modification, where mammoths would create windbreaks, clear feeding areas, and even construct what appear to be primitive shelters using available materials. But mammoth intelligence extended beyond simple survival strategies. These creatures developed what can only be described as cultural traditions that varied between different geographical populations. Tusk wear patterns, feeding preferences, and migration routes all show regional variations that were clearly learned behaviors rather than genetic adaptations. This cultural diversity represents one of the most sophisticated examples of non-human society ever documented in the fossil record. The late Pleistocene also witnessed the emergence of Smilodon fatalis, the most famous and successful of all saber-toothed predators. But calling these creatures simply saber-toothed tigers dramatically understates their revolutionary approach to predation. These were pack hunters that combined the social intelligence of wolves with killing capabilities that exceeded anything in the modern world. The hunting strategies employed by Smilodon packs represent the pinnacle of cooperative predation in mammalian evolution. These weren't simple mob attacks by multiple individuals. These were coordinated military operations that required role specialization, tactical planning, and precise execution. Fossil evidence from tar pit sites reveals injury patterns that could only result from highly organized group hunting behaviors. The social structure of Smilodon prides was more complex than that of any modern predator. Evidence suggests these cats developed hierarchical systems with specialized roles including scouts, ambush specialists, and support hunters that would care for injured pack members. The level of cooperation required for such social organization indicates cognitive abilities that approach those of modern social primates. What makes Smilodon particularly remarkable is the evidence of cultural transmission within prides. Hunting techniques, territorial knowledge, and survival strategies were passed down from experienced adults to younger generations through what can only be described as teaching behaviors. Cubs would spend extended periods learning complex skills that required practice and refinement over months or even years. The success of Smilodon created what researchers call a terror landscape, where the mere presence of these predators influenced the behavior and evolution of every other species sharing their territory. Herbivores developed enhanced vigilance systems, escape behaviors, and defensive strategies specifically designed to counter saber cat attacks. This predator-prey arms race accelerated evolutionary change throughout late Pleistocene ecosystems. As we approach the end of the Pleistocene epoch, around 12,000 years ago, we encounter the final chapter in our journey through post-dinosaur evolution. The ice ages were coming to an end, global temperatures were rising rapidly, and a new species was emerging that would ultimately reshape the entire planet according to its own vision. The late Pleistocene extinction event, often called the Quaternary extinction, marked the end of the age of giants that had dominated Earth for over 60 million years. The magnificent creatures we've encountered throughout our journey, from the massive predators of the Paleocene to the intelligent giants of the Pleistocene, were facing their final challenge. And unlike previous extinction events caused by asteroid impacts or volcanic eruptions, this one had a very different cause. The emergence of modern humans during the late Pleistocene created competitive pressures unlike anything Earth had experienced since the original dinosaur extinction. These weren't just another predatory species competing for resources. These were tool-using, fire-making, landscape-modifying engineers that could adapt to any environment and exploit any available resource with unprecedented efficiency. The cognitive abilities that had allowed mammoth herds to survive ice ages enabled saber-cats to coordinate complex hunts and permitted marine mammals to thrive in the ocean giants to navigate vast oceans, suddenly seemed primitive compared to human intelligence and technological capabilities. For the first time since the asteroid impact 66 million years ago, Earth's dominant life forms were facing a challenge that couldn't be solved through physical adaptation or behavioral modification alone. But the story of post-dinosaur evolution isn't simply one of extinction and replacement. Many of the innovations we've encountered throughout our journey through deep time continue to influence life on Earth today. The intelligence and social complexity that emerged in Pleistocene mammals provided the foundation for modern ecosystems. The predatory strategies developed by ancient carnivores continue to shape the behavior of contemporary species. And the environmental engineering capabilities pioneered by extinct giants established ecological principles that still govern natural systems worldwide. The creatures that dominated Earth after the dinosaurs weren't just evolutionary experiments that failed to survive changing conditions. They were pioneers that pushed the boundaries of what was possible in biological systems. They developed intelligence levels that approached human capabilities, created social structures that rival modern civilizations, and engineered environments in ways that supported unprecedented biodiversity. Their legacy lives on in the DNA of every modern mammal, the structure of contemporary ecosystems, and the evolutionary principles that continue to drive biological innovation. The age of giants may be over, but the influence of these magnificent creatures continues to shape life on Earth in ways we're only beginning to understand. From the tiny mammals that scurried through the darkness after the asteroid strike to the magnificent giants that ruled Ice Age landscapes, we've witnessed an evolutionary story that spans over 60 million years of Earth's most dramatic transformations. These weren't just random creatures filling empty spaces left by dinosaurs. These were intelligent pioneers that pushed the boundaries of what was possible, developing hunting strategies, social structures, and survival techniques that modern science is only beginning to understand. Here at Ancient Dreamser, we believe these forgotten titans deserve to be remembered not as evolutionary failures, but as the architects of the natural world we know today. Their legacy lives on in every heartbeat of modern life, reminding us that intelligence, adaptability, and cooperation have always been the ultimate keys to survival on this ever-changing planet.